Welcome to the e-lecture session for diploma students. In today's class, we are going to see some of the merits and demerits of armature control or resistance control method, which we have discussed in the previous class. Number 1, this method is not widely used because of the large losses in the rheostat, and also efficiency of the motor gets reduced. Number 2, speeds below rated speed can only be obtained in this method. 3, requires expensive arrangements to dissipate the heat developed in the control resistance. Number 4, this method results in poor speed regulation. Then comes the merits. This method is suitable for constant load drives, where speed variation from low speed up to rated speed are only required. Then comes the field control method. As per the speed equation, the speed is inversely proportional to the field flux. Since the flux depends upon the exciting current, that is the field current, if the current is decreased, then the speed will increase. In the field control method, the air gap flux is varied by introducing a resistance in the shunt field circuits. It is most commonly used method. Here is a schematic diagram of the shunt motor. Here we are going to include a field resistor for speed control. So, you can see here it is the characteristic curve between the speed of the motor and the armature current. So, this is the speed with field rheostat, and this curve represents the speed without field rheostat. Suppose if the field rheostat is not added up here in the field, what happens here is the speed obtained is much lesser than the actual one. Here already you have added up a field rheostat, that is the variable rheostat. Now you can vary the magnitude of resistance of the shunt field circuit. So, once this field rheostat is included with the shunt field resistance, then ultimately your resistance of shunt field will increase. Now, I will show. Now, here what happens is RSH is the actual shunt field resistance. Now, what happens here is you are going to add some more resistance, that is field rheostat resistance, let us call it as RF. Because of increase in resistance, what happens? The current, that is field current, will reduce. Because of this increase in resistance, field current will reduce. Once field current is reduced, what happened to the flux? Flux will also reduce. Once flux is reduced, what happens to EB, that is N? N is directly proportional to EB by phi. So, once flux is reduced, since the magnetic flux being produced is inversely proportional to the speed of the rotation of the motor, to compensate this, the speed of rotation will increase. So, this is clearly depicted by this curve. This is the speed without the field rheostat. Once the field rheostat is included here, the net effective resistance across the field is increased. So, the net effective current across the field is decreased. Because of that, magnetic flux is getting decreased. Once magnetic flux is decreased, the speed of rotation gets increased. So, this is the speed of rotation of the motor by including a field rheostat. So, you can increase the value of speed by introducing the field rheostat here. So, that by varying this you can attain any number of speeds here. A variable resistance, a rheostat is connected in series with the shunt field of shunt or compound motor. By increasing the series resistance, the field current may be decreased, and thus the field flux weakens and the speed increases. In this case, losses are very small. In this method, we can only raise the speed of the motor above the rated speed. Since the flux cannot be increased beyond the value corresponding to the rated voltage. So, these are the few advantages. What are the advantages? One is higher speeds, that is above the rated speed can be obtained. So, this we can this we have already practically verified with the characteristic curve in the previous slide. Speed control is easy, economical, convenient and efficient. The speed control by this method is independent of the load on the machine. Whatever may be the load, the speed control can be easily achieved by this method. So, that is one of the biggest advantages of this method. So, here are the few disadvantages. At high speeds the flux will be very low and the torque is also reduced. So, this is a very important point which should be kept in mind. So, at very high speeds what will happen to the flux? Flux is inversely proportional to the speed. So, at very high speed the flux will reduce. When once the flux is getting reduced, ultimately it will have an adverse impact on the torque also. Torque is also getting reduced. Number 2, there is a limit to the maximum speed obtained by this method, as the weak field leads to poor commutation. Then speed control of DC series motor. So, the methods employed in the speed control of DC series motor are: one is a field control method and the other one is a field diverter method. Here you can see a variable resistance called diverter is connected in parallel with the series winding as shown in figure 2.2. You can see here. So, this is the field winding. Here we have connected a variable resistor called as a diverter. So, this is the armature current. So, this is the supply, this is the armature current. Once the armature current reaches this particular node, the entire armature current will not flow through the field. So, a part of this armature current will flow through the diverter. So, it is getting diverted here and then it is coming back at this node. At this node again IA will travel through the armature and then through the entire circuit. So, what is the purpose of diverting the current through the diverter is, we are going to change the current passing through the field. Once the current passing through the field is changed or reduced, we can have a direct impact on the magnetic flux. Once the current passing through this field is reduced, magnetic flux will reduce. Once the magnetic flux is reduced, ultimately the speed of rotation will be increased. So, this is the idea of incorporating a diverter across, or you can say in parallel to the series resistance. Any desired amount of current can be passed through the diverter by adjusting its resistance. The flux can be decreased and hence the speed of the motor is increased. This method can provide speed above the rated speed. The lowest speed obtained is the rated speed of the motor. Suppose if the rated speed of the motor is 1500 revolutions per minute, any speed above 1500 can be achieved by this method. So, this is what it says. Applications: this method is mainly used in the speed control of electrical trains. By this method, speed above the rated speed only could be obtained and the power loss in the diverter is quite considerable. Then comes the armature resistance control method. In this method, a variable resistor called armature diverter is connected across the armature. So, this is somewhat different to the previous one, whereas we are getting a diverter across the field coil in the previous slide, whereas here we are having a diverter across the armature, that is in parallel to the armature. By this method, the armature current is controlled to vary the speed below the rated value of the series motor. For a motor running at constant load torque, if the armature current is reduced by the armature diverter, the line current increases to meet the torque and the series field current increases. This increased field current reduces the speed. This method is costly and unsuitable for changing loads. The speed control method illustrated for DC series motor cannot be used for compound motor, as this adjustments would radically change the performance characteristic of the compound motor. Now, this is one of the methods employed for series motor speed control. What is this? Actually, it is a field tapping method. So, we are not going to include any diverter circuit here. Instead, we are going to have a control over the field tappings, that is the number of turns connected to the motor. A tap changing arrangement is made on the series field winding as shown in this figure 2.24. By varying the number of effective turns of the field winding, the speed can be controlled. The motor circuit should be started with all the winding included, and the speed can be changed then by setting a suitable tappings. Suppose if I keep this tapping over here at this point, no turn will be included. On the other hand, if I keep the tapping here at the left extreme, then all the tappings will be included, no tappings will be included. So, by this way you can control the number of turns to be included in the circuit. Now, if the number of turns is minimum, then what happens? Now, the current passing through this will be more. If the turns are more, then the current will be less and vice versa. So, when the current is more, what happens to the magnetic flux? The magnetic flux will also be more, which will have an impact on the speed of rotation of the motor. We have already seen this. Otherwise, if the tapping is kept at lower setting and the motor is started, the motor races to a very high speed at the time of starting itself, which is undesirable. This effect we have already seen in the characteristics, that is speed characteristics, speed current characteristics of DC series motor, because the series motor is not supposed to start at no load. We cannot afford to start the DC series motor at no load, because the speed will be much higher. Applications: this method is used in small motors like food mixers, fans, etc. This method has the following disadvantages: number 1, poor speed regulation; number 2, power loss in the series resistance. In spite of these disadvantages, this method is most commonly used, since it is only used intermittently when the motor is carrying full load. At that this is the necessity of starter. So, this is a very important topic while studying the motor characteristics. What happens if a motor is going to be started without a starter? So, this is the significance of the starter. So, what happens here is, at the time of starting, speed of the motor is 0, that is n is equal to 0. So, what happens to the back EMF then? Back EMF is also 0, that is counter EMF produced across the armature is also 0. So, when EB is 0, what happens to I? IA is equal to V minus EB by RA, we know this equation. So, if EB is 0, since RA is very less, it is in the order of 0.5 or 0.8 ohms, V will be, say for example, if it is 220 volts, then 220 by 0.5 will yield you 440 amperes, which is much higher. So, we cannot afford to start a motor like this. So, what we need to do is, at the time of starting, the speed is much lesser, so, speed is almost 0. So, we need to have a mechanism to check this magnitude of current. So, when motor is not starting, when the motor is at 0, that is the rotation of the motor is 0, then what happens here, EB is 0. So, in order to compensate the value of EB, we need to include much more resistance, say for example RS. I need to include a resistance, much higher resistance here. Then what happens? So, the resistance in the denominator side is much higher, then the current IA will be coming to a considerable value, less value. So, this is a small arrangement, so ad hoc arrangement till EB is developed, then this RS value will be taken out. So, slowly there is a mechanism called as a starter by which you can change the handle right from the beginning. So, earlier the resistance will be, maximum resistance will be connected to the handle. Once you move the starter like this, the resistance will be cut simultaneously and only the resistance Ra will be present. By the time the motor will start to run, once the motor starts running, keep running, then EB will be developed. So, this difference V minus EB will be less value, which will yield a less armature current. So, this is being explained here. The current drawn by the motor from the rated supply voltage will be several times the rated current, since the back EMF is 0 and the armature resistance may be less than 1 ohm. This heavy starting current leads to the following problems. One is heavy sparking at the brushes, which may destroy the commutator and brush gear. Number 2, sudden development of large torque causes mechanical shock to the shaft, reducing its life. Number 3, insulation may get weakened due to the heat produced by the high starting torque, because the energy being developed will be I square into R into T. Then comes the types of DC motor starters. 2-point starter is employed for starting of a DC series motor, 3-point starter is employed for DC shunt motor, and 4-point starter for DC compound motor. Now, let us see the configuration of 3-point starter as well as the significance of 3-point starter in starting a DC motor. So, this 3-point starter has 3 terminals, namely L, that is line, field F, armature A. Number 2, a handle with a soft iron keeper. Number 3, overload relay OLR and no volt release coil NVR. So, this is the schematic diagram of the 3-point starter. The connection diagram of a 3-point starter is shown in the figure 2.26. The starter terminals to be connected to the motor are armature A, field winding and line L. The starting resistance is arranged in steps between conducting raised studs. As the starting handle is rotated about its fulcrum, it moves from one stud to the next. One resistance step is cut out and it gets added up to the field circuit. There is a short time wait at each stud for the motor to build up speed. This arrangement ensures a high average starting torque. So, when the handle is at this point at the start of the motor, maximum resistance is included across the armature in series with the armature. Once the handle gets moved from here, slowly all the resistance will be cut. Once it reaches this point, by the time the motor attains the rated speed, so that EB is developed, so that Ia will be reduced. Only during starting all the resistance will be connected in series with the armature. At the start the handle is brought to the stud 1, the line voltage gets applied to the armature with full starting resistance in series with the armature and to the field with no volt coil in series. Thus, the starting current is limited to a safe value and the motor starts with maximum torque. As it picks up speed, the handle is moved from stud to the on position as shown in the figure 2.26. The starting resistance has been fully cut out and is now included in the field circuit. So, this is the position, the final position of resting position of the handle. Being small, it makes little difference in the field current. The resistance of no volt coil is small and forms part of the field resistance. The voltage across the armature is the line voltage. The handle is held in this position by the electromagnet excited by the field current flowing through the no volt coil. The two protections are incorporated in the starter. One is the very important no volt coil and the other one is overload release. No volt coil, in case of failure of field current due to accidental or otherwise open circuiting, this coil releases the handle which is being held electromagnetically and goes back to the off position under a spring action. Overload release, the contact of this relay at armature current above a certain value, overload or short circuit, closes the no volt coil ends, again bringing the handle to off position due to demagnetizing of no volt coil. Disadvantage: if the motor speed is controlled using field regulator, the no volt release gets de-energized and the handle goes back to off position. So, the field control cannot be applied in 3-point starter. 4-point starter, it has 4 terminals, namely L plus, L minus, field F and armature A, and a handle with a soft iron keeper, overload relay and no volt release coil. Then we will move on to the power stages in a DC motor. The power stages in a DC motor are represented diagrammatically. So, this is the input, I will zoom it on, you can see here. So, these are the power stages in a DC motor. This is the input. After copper losses, this is the mechanical power developed in the armature. By subtracting the friction and friction and iron losses, you get the output power of the motor here. So, this is block A, block B, then block C. Now, A minus B will give you the copper losses, B minus C will give you iron and friction losses. The mechanical efficiency is given by eta m C by B, electrical efficiency B by A, and the overall commercial efficiency is given by block C by block A. Now, we will get into the losses in a DC machine. The losses taking place in a DC machine are copper loss, magnetic loss, mechanical loss. Now, copper losses, armature copper losses given by the expression Ia square Ra, where Ia is the current in the armature, Ra is the resistance of armature and interpoles. This loss is about 30 to 40% of full load losses. Then comes the field copper losses. Shunt field copper losses is given by the expression I square SH RSH, where ISH is the current in the shunt field winding, RSH is the resistance of shunt field winding. Then series field copper losses, ISE square RSE, where ISE is the current in the series field winding, RSE is the resistance of series field winding. There is also a brush contact loss due to the brush contact resistance, that is the resistance between the surface of brush and surface of the commutator. This loss is generally included in the armature copper loss. Then comes the iron or core losses. These losses occur in the armature of a DC machine and are due to the rotation of the armature in the magnetic field of the poles. They are of two types, one is hysteresis loss, the other one is eddy current loss. Hysteresis loss occurs in the armature of the DC machine. Since any given part of the armature is subjected to magnetic reversals as it passes through successive poles, it is given by the expression hysteresis loss is equal to eta b power 1.6 max f into V. So, f is the frequency of magnetic reversals, this eta is nothing but it is a Steinmetz coefficient. Here you can see B max is equal to maximum flux density in armature in Weber per meter square, f is the frequency of magnetic reversals, V is the volume of armature core in meter cube, eta is the Steinmetz hysteresis coefficient. In order to reduce this loss in a DC machine, the armature core is made of such materials which have a low value of Steinmetz hysteresis coefficient. That is, example, we can have the armature core made up of a silicon steel to reduce this hysteresis loss. Then comes the eddy current loss. When armature rotates in the magnetic field of the poles, an EMF is induced in it which circulates eddy currents in the armature core. The power loss due to these eddy currents is called eddy current loss. In order to reduce this loss, the armature core is built up of thin laminations insulated from each other by a thin layer of varnish. Here eddy current loss is given by this expression Ke B square max F square T square V watts, where Ke is a constant, B max is the maximum flux density in the armature core expressed in Weber per meter square, F is the frequency of magnetic reversals in hertz, T is the thickness of lamination in meter, V is the volume of the armature core in meter cube. It may be noted that the eddy current loss depends upon the square of lamination thickness. For this reason, the lamination thickness should be kept as small as possible. Finally, the mechanical losses. These losses are due to friction and windage effects. Friction loss, example, bearing friction and brush friction, etc. Windage loss is due to air friction or rotating armature. These losses depend upon the speed of the machine, but for any given speed they are practically constant. So, iron losses and mechanical losses together are called stray losses. So, before concluding this session on the various DC motors, we will have a quick recap of whatever we have learned today. So, in today's class we have seen the necessity of a starter in a DC motor, we have seen the working of a 3-point starter and the significance of starters and various characteristics of DC motor, applications, merits and demerits and the various losses involved in a DC motor. Thank you.